Yeah, so welcome to the webinar, and I'm going to walk you through the webinar today. And let's start first with some business challenges. So typically what we see is that electronics get smaller and smaller. Devices get smarter means that they need more CPU power. You have the ubiquity of devices, and of course, everything is getting more connected. We can see that 55% of the issues that we have with electronic devices lead from thermal issues. But also dust and humidity can be covered with CFD simulations. And therefore, it's almost 80% that you can cover with simulations for CFD. Manufacturers worldwide face challenges such as, of course, they want to lower the development cost, faster time to market, more innovative and better performing products, as well as bottlenecks in the design processes that need to be addressed, and reduced operational risk and compliance, especially in safety critical electronics or medical equipment. What we usually see is only the tip of the iceberg when it comes to the development cost. The larger part we often don't see is what happens beneath the waterline. Things that happen during the development process at a later stage can increase immensely the costs onto your development process. So 5 top hurdles that product design have, and what the best-in-class strategies are, what the best-in-class companies are doing. The top hurdles are, for example, problems and errors that are found too late. Next, making trade-offs by cost, performance, and quality, or the frequent design changes because you want to test something new. There's a new idea how you can fix things, and they can happen quite frequently. Predicting product behavior in the real world and environment, and of course the workforce reduction or the lack of technical experts. Now, how big the top best-in-class companies usually address it is by putting the analysis of the product behavior very early in the design cycle, implement get it right first time strategies, and promote the collaboration between the analyst experts and the design engineers. Evaluate more design iterations in the concept and design stage, so therefore addressing the frequent design changes, and define best practices for assessing product behavior. And of course, you want to reduce the unique parts in your product. So what you really need is the front-loading approach. So let's have a look at what Siemens is understanding on the front-loading approach. With SimCenter Flow EFD, we have a lot of experience, and it's deployed across a lot of industries and applications. You can see here mixing fluid, refrigerants, electronics cooling, which is what we're going to cover today, aerodynamics, free surface, joule heating, supersonic on the bottom right, but also applications such as cavitation, condensation, in this case, and the headlight here. But also in electronics, condensation is a critical topic. Heat exchangers, rotating equipment such as fans and pumps, PCB modeling, also electronics cooling, combustion modeling, like you can see on the bottom left, in a jet engine fire, radiation either from sun or from hot equipment, and non-Newtonian flow. That might be the encapsulating of a semiconductor, but also extrusion modeling and ventilation, either in electronics, of course, but here in this example, we can see the ventilation of an office building. And aero heating, where, for example, you have a rocket flying at high Mach number. There's electronics on the inside, but the friction of the air on the outside is causing the rocket to heat up, which will then, of course, impact the electronics as well. So since we know that electronics nowadays plays a big role in almost all the products, we have to consider them in any type of environment. Now, when we come to the Siemens front-loading approach, we see that with SimCenter Flow EFD, since it is a fully CAD-embedded CFD solution in NX, Solid Edge, CATIA V5, and Creo, we are giving the design engineers the possibility to run simulations very early in the design cycle. There is no need to simplify the geometry. Of course, you can do that to save mesh and CPU time, but not because of the software requires it from you. because it's getting too complex that it won't mesh or anything like that. It's really just because you might save some time for the CPU of the calculation. The smart cell technology, which I'm going to come in a second to, is minimizing the user time that needs to spend on meshing. The meshing is done fully automatically. The user just might need to define a local region here where it needs to be a little bit finer, or this component. But besides that, the meshing is done fully automatically. The accurate and robust solver technology that is connecting to this type of mesh, you will see in a second. And of course, the design exploration. You want to test new ideas. What happens if I change it this way or this way? How many ribs does my heat sink need? And this type of design explorations is what you can do very early. Now, if we look at electronics applications, you can see there's, of course, power electronics like IGBTs, ADAS cooling in the automotive industry. You have lighting like with LEDs or regular bulbs that produce a lot of heat. I have also a story on that later on. Medical equipment, of course, telecommunication, charging, especially now with electric vehicles. You want to have fast charger, sensors in LiDAR, ECUs, so engine or electronics control units, and small devices such as security cameras and household devices. Now, if we look at the technologies that SimCenter Flow EFD is offering, there are basically two key areas. One is the solver, which is augmented with special engineering and empirical and analytical models, but it uses the traditional numerical approaches as a foundation. So there's nothing new about that. We use runs, Reynolds average, Navier-Stokes equations with wall functions, but then with the SimCenter Flow EFD, we add extensions which we call the smart cell technology. That includes a particular type of meshing, the Prandtl boundary layer model, analytical equations, and empirical models that are all working together. The solver is automatically deciding which approach is being used depending on the mesh type at that location or the mesh size. Now, the second one is the CAD embedding. So since SimCenter Flow EFD is fully embedded in the CAD system, it enables to have the whole simulation being done by the designers really in their environment. So let's come to the smart cell technology first. There are three major types that we have implemented. One is called the thin boundary layer. There's a thin and a thick boundary layer, and the solver automatically decides which one is going to be used. The thin boundary layer is, for example, used if the mesh size, as you can see here, is not resolving the boundary layer. It automatically then switches to the thin boundary layer and is still getting accurate results. So this avoids the user to need to spend time on how big is my boundary layer? Do I have a Y plus value that is high enough that I can resolve the boundary layer accurately and so on. This takes away that numerical knowledge that the user might need and puts it onto the solver side. The thin walls is representing very thin features. Like you can see up here, the blue layer in here is within one cell. You have the green, dark blue, and bright blue layer basically within one cell. So the cells can contain multiple control volumes within a cell. You can also see down here that you have one large cell covering multiple of these spring-like rings here. And in between, there's always a fluid. So you have solid fluid, solid fluid, solid fluid, and so on within one single cell. That also enables that you don't have to spend a lot of time of refining such small features, small geometries. The meshing just meshes over it. And depending on the resolution that you set, you get high resolution or low resolution. But the approaches that are used, like the thin boundary layer or the next one, the thin channel, will still achieve your high accuracy. The thin channel, you can see up here, there's one cell between the heatsink ribs. Up here are two cells. But in general, this usually wouldn't be something that you would use in traditional CFD tools because it doesn't resolve what's happening between the ribs. In SimCenter Flow EFD, we have the thin channel technology. You can see that also down here, which is the brown one is a heat source. and then you have a meander cooling going around here in these channels. You can see, for example, there's about 2.5, 3 cells in the first one. In the second one, we have about 5, so it always doubles here, and then we have about 10, 11 cells. And you can see that amount of cells, 250,000, 610,000, or almost 1 million. But the results in temperature difference on the water side, pressure difference through the water side, as well as the heat into the water is not really making any difference. So this thin channel approach applies automatically if the mesh is not resolving such a channel in all the detail. It automatically uses a thin channel approach and still gets accurate results. And then coming to the CAD embedded side, as I mentioned already, we have NX, Solid Edge, Creo, as well as CATIA integration, and it automatically recognizes here the fluid volume. So the user doesn't have to work with a negative. If he designs the CAD model, he usually designs it in the positive, and he can then directly use it as it is. He doesn't have to extract the negative, the fluid volume. And everything he does in a CAD system is always in sync with the simulation. So when he changes the CAD system, as you can see here, if he changes the geometry and is done with it, the simulation tool will ask him, do you want to maybe make the computational domain bigger if the geometry was getting bigger and therefore is outside of the computational domain? You click on yes or no, but it always is in sync with the design. And you just have to rerun the simulation if it was already set up and you just made some changes to see what happens. The pre and post processing, as you can see, is fully done within the CAD system. So at no point the user is leaving a CAD system. He can design, run the simulation, do the post processing in the design tool, and then continue with his design experiments with the changes that he wants to do. And with that, it all is the look and feel of the CAD system which the user is familiar with. And as you can see, there's no simplification of the geometry necessary. You can see there are screws in there which have the cross of the screw head. If the mesh is not fine enough to resolve the cross that fine, it just meshes over and you have a very coarse screw head. But you don't need to simplify it. Of course, also design engineers want to do design exploration. So there are multiple ways of doing that. There is, for example, the what-if analysis, where you can run a range of parameter steps where you want to see how many ribs do I need, 5, 10, 20, 50. You can run such simulations. A goal optimization, such as changing the flow rate of the fan inlet to a value where the chip temperature reaches 50 degrees. So then you know, okay, at this flow rate is what I need. So I can go into my fan database and look for a suitable fan and then put that in as a fan curve and see if the fan curve also gives the same result. DOE and response surface simulation, as well as external optimizers, such as linking to heat and DO, but also other external optimizers if you already have some in-house to optimize the CAD geometry as well as SimCenter FlowFD boundary conditions and see if you can find the optimum for your design. Multi-parameter optimization is an additional module for FlowFD where we basically use the Heat Sherpa solver. It's kind of a light version of Heat, so it's not as powerful as Heat, but you get the optimization capabilities to change geometry as well as SimCenter FlowFD boundary conditions. Characterization, so that it's a more of a 1D approach for system simulation, which is typically not very used in electronics cooling. So I'm not going to go into that much detail here. The more important one is the calibration part, but I'm going to touch on that a little more detailed, so just being mentioned here. Now, let's have a look at the electronics cooling functionality of SimCenter. Well, when we talk about electronics cooling, we're usually talking about some PCBs with chips on them, and of course, at some point, a fan or heat sink. But it all usually starts with a PCB and the components placed on them. So you need to be able to import the EDA files that might be from Expedition through ODB++ files, IDF, ProStep, and so on. And for that, we have the FlowFD EDA bridge. This is a module where you can import these files and then get them into the CAD system as 3D models, because you might not have them, or you might just have a simple block for the PCB. This get all the information that is contained in the EDA file into SimCenter Flow. You can even see down here, there's a copper trace model in 3D explicitly in SimCenter Flow FD. So you can choose if you want to import explicitly as a compact model, so just a simple block of PCB, or there's a new feature, it's called material map, which then leads to a SimCenter Flow FD boundary condition called Smart PCB, which I'm going to show you also in a second. So here, this is the Smart PCB. What it does, it imports basically the picture of the PCB, of the copper traces, and then pixelates them. So every pixel is basically represented by a thermal network. You have a thermal resistance, thermal capacitance, depending on the material that you use, and the dimension or the accuracy of it can be controlled by the user by making it very coarse pixelated or very fine. The beauty of it is it's only a voxel mesh. It doesn't require a CFD mesh like you can see here on the right. The mesh used here is as fine as you can see it here with the details. The CFD mesh is much coarser, and you can just use it in the same mesh because it's independent from the CFD mesh. Just as an example, if we take this PCB, you have, of course, copper, you have FR4, you have copper again, or different materials. And the FR4 is, of course, a not so good heat conductor compared to the copper. If you would use that as an average material, import it as a, compact model, you have an average material property, and that, of course, is not as well as copper or as bad as FR4. So it's averaged and therefore not as accurate. We might get a CFD mesh that is 130,000 cells big. The import time from the EDA bridge is 1 minute. The meshing time, 1 minute, and the solver time, 5 minutes. And you get, if there are 3 chips on them, you get 91, 95, and 80 degree. If you look at an explicit import, so you get all the, at least the major copper traces in detail as 3D structures, and you need to mesh them in detail. So the importing will take some time because the geometry has to be created of all the copper traces that you import. The preparation time, which is the meshing time, also takes longer. It's automatically done, but it needs to mesh a lot more geometry, and you need to have a much finer mesh. So we're talking about 8.3 million cells. And then you have a CPU time of 7.7 hours. And if we assume this is the most accurate resolution, and therefore accurate compared to experiments, we get 122, 130, or 103 degrees Celsius, and you can see the difference between the average model. Now, the Smart PCB is running on a much lower mesh cell, so almost about 100,000. The import takes a minute, meshing takes a minute, just like with the average. The CPU time takes 70 minutes because you are calculating the thermal network model in here. It's not as simple as the solver time for the average one, but you get very high accuracy in the results already, much more accurate than compared to the average one. This, for example, just shows you the detailed, the explicit modeling, where you can see the copper traces here in detail with the heat source of the chip. So it's like this model here, where you can see the copper traces in here actually modeled explicitly in 3D copper traces. And then also, of course, compared to the thermal camera, where you can see it has the same temperature field as with the simulation. Now, here's just a small example of how that would look like. So if I would look at my simulation model, this is the import of the EDA bridge for this medical device. So you can see that the PCB is missing here. We're going to import that from a file. In this case, it was an expedition file. You can see there's all the components in here. And we're going to import a thermal list, which basically is a CSV or Excel file with all the thermal loads onto the components. You can see them here distributed over the components. And then when I import that into SimCenter FlowFD as a material map, we will automatically create the PCB as a 3D component. That's what you can see here now. It's going to be created. And on the left side, it automatically creates also the project because you already have the heat sources defined, and then it gets imported into your simulation model. Once you run it, you get all the results with the heat sources applied to the components and can simulate it with the housing and everything. And if we look now at the smart PCB that was imported, you can see it in the tree down here. And if we look at one of these layers and visualize how that looks like, you can see this is the detailed and very fine representation, but you can tune from fine to average or set your own accuracy, and you will then see the pixelation change being much coarser. Yeah, and this is basically how the smart PCB is then getting used in the simulation as a thermal network model. Now, of course, joule heating, as I mentioned, is important as well for some high power or high current flow that might be also either through some copper traces in the PCB, but also you might have some wires like here in the power charging application where you have the connectors here where the minimal surface connection is, and therefore the hottest temperatures appear here at the connector side. You can see there's some hidden cooling loops going around it because at high power charging or fast charging, you have the need to cool these connectors. Otherwise, they get extremely hot, might melt over time, and this is something you want to avoid. So here you can specify currents and voltage types, up here voltage or resistance between components, and then run the joule heating simulation. So all of these simulations are coupled automatically. So fluid flow, heat transfer, joule heating, you just run the solve and the solve solves all of them. Now, of course, one other, major component on PCBs is the chip, the semiconductor. So there are multiple ways of simulating or modeling them. The simplest one is simplified block. You have material applied to it, a certain heat load, done. A little more advanced one is a two-resistor model with junction board, junction case, and of course the network assembly, a Delphi model where you can define junction to top outer, top inner, between them, with the thermal resistances between them. If you have that detail, you can apply that as well. Or of course the explicit one in all its detail, including wire bonds, and this is something you might be interested to do. And you can either import these models or create them yourself in detail, or there is a package creator module for FlowFD, which I'm going to show you here. So the package creator is an additional application where you can select from an array of different, templates, a certain type of package, and then you can define encapsulant die attach, and so on in all its detail, with number of pins or thickness and length, width of the die, and so on, to get your detailed 3D package that you can then import in SimCenter FlowFD. Now let's have a look at how that looks like. So this is the user interface of that package creator, and if you get a create package, you can pick from one of these templates and then redefine it in more detail. You can see all the different structure. You can change the values. You can say how many pins you want to have, if detailed or compact, and then save that component and import it into SimCenter FlowFD, either like here in the empty assembly or into your PCB, where you then just have to place it onto the right position. You can see we have the boundary conditions of materials being imported automatically, as well as the heat source. And of course, you can adjust the heat source if you need it for different power. I already mentioned the calibration. Maybe I need to introduce you briefly to another measurement equipment called Twister, which is also something from the SimCenter product line. It's for thermal characterization of semiconductors. So what you get from the experiments here is a structure function, which is an RTH-CTH curve from the die into the environment. Each layer will be represented as a RTH-CTH step in here. And if you want to have a detailed model, but you don't have any models from the supplier and so on, but you have the physical element of the IC, you can test it with a SimCenter Twister, and you get the structure function. If you know roughly about the dimension and design and the amount of layers that you have in your model, you can model it roughly in the CAD system. And then with the automatic calibration, you can match these parameters like length, width, thickness, or material properties to match the measured curve. So you start with a first draft that you have defined, and you specify which parameters can it change. And then it runs automatically changing these parameters and matching it to the measured curve. And therefore, you have then a calibrated thermal model that you can use in your future simulations of this IC package, for example. Another nice feature is the BCI ROM extraction. BCI stands for boundary condition independent, and ROM is very famous right now, the reduced order models. So it's a boundary condition independent reduced order model. What does it mean? It basically means you apply boundary conditions such as a heat source, but the actual value doesn't matter, because if that value is actually controlled by another system simulation tool such as MATLAB or GNU Octave. So SimCenter FlowFD, you apply the boundary conditions, materials, and so on, and then the ROM is extracted, and you run that in MATLAB, for example, where you get the loads, the heat sources, and so on applied to the ROM, and it solves here up to 40,000 times faster than if you would solve it in a 3D simulation. Especially in transient simulation, like this drive cycle that you have as a boundary condition onto the IGBT. It maybe takes half an hour for the drive cycle, but has very fine transient behaviors, which are very hard to simulate transient over that long time very efficiently. And with the BCI ROM, you get that done about 40,000 times faster. So let's have a look on how that looks like. So you can see there are materials as well as hot and cold side applied, or you have then the IGBT boundary conditions for the heat sources and some point goals which at the end get you the temperature of the individual components. You extract the ROM where you specify the error, the maximum and minimum heat transfer coefficient, so basically either liquid or gas cooling, and then you create the BCI ROM. This file then can be directly used in MATLAB or GNU Octave. You can see here the files that are getting created. And then MATLAB or GNU Octave is solving that based on the boundary conditions that MATLAB and GNU Octave apply to it. Another one is the netlist. Netlist is a thermal electric solver. It basically works the same way. You export the netlist as a file, which is a SPICE file. So every SPICE simulator that supports these files can use that for thermoelectrical simulation. So it's also a reused order model, not as the BCI ROM for use in system simulation tools or mathematical tools like MATLAB, but for SPICE simulators as an electrothermal. A very nice feature as well is the flux plot, where you can then visualize the heat flux between each and every component or layer of your model. So you have, for example, the copper dielectric substrate, the tin material, and the heat sink assembly then going into the environment, and you can see how much is radiated from this component, how much heat is transferred through conduction or through to the environment via natural convection. So you can see very detailed, nicely, how much energy is transferred from what component to what. And in this example, we're looking at the DOE simulation that we did for this heat exchanger with 2 LEDs in it. And when we run the DOE, we have 18 variables. So those lead to 90 design points. Each simulation takes about 5.4 minutes, but it's run completely automatically, and then you get a wide range of design variations. And you can pick at the end either by the minimum heatsink mass or the minimum temperature. This is up to the user where his preference or his well-designed target lies. With a minimum temperature, minimum mass, you might not get the minimum temperature. With a minimum temperature, you might get a very high mass. So this is up to the user then to decide which fits best into his spec sheet. And last but not least, of course, a lot of electronics is driven by batteries. So also here we can do battery cooling, where you can see the state of charge or the temperature of the battery in transient with a electrothermal models of the batteries represented here. So you can also do battery cooling for your electronics if you have some power tools or electric vehicles and so on. Good. I think you have seen a lot of capabilities of SimCenter FlowAFD, but let's have a look at some of the successes that our customers have. One, for example, is Psycho Epson. I think everyone knows Epson, the projectors or printers. And here you can see the geometry complexity of such a projector on the inside can be quite big. And depending if you use LEDs or some bulbs, you have radiation, some more, some less, depending on what type of light source you're using. But also a lot of electronics, like some transistors or chips that need to be cooled. And what Epson, for example, here says is SimCenter FlowAFD is essential in our daily work. In many cases, we can't predict the results of the analysis, but SimCenter FlowAFD leads us to correct results automatically. Automatically because of that automatic meshing and also, of course, stable and converging solver. AEG, so some power tool applications here, where you have then electric motor, maybe some wires going through here as well with a little bit more current going through, and of course complex geometry on the inside and compact. There's barely any space for airflow and so on, and you have then a fan driving the air through the device. And they say, as power tools are getting more compact, we investigate motor cooling issues to better understand the effectiveness of the cooling method used. We choose SimCenter FlowAFD because it's easy to use. Danfoss drives, they're looking into IGBT cooling for applications such as wind power plants, where you have then the IGBTs controlling the frequency to put it into the net. And you can see here their cooling platform here, the bluish part in here is what they are designed. It's called the shower power. And what they say is, I like SimCenter FlowAFD compared to other more complicated CFD tools because I can dip in and out in it all year with minimum effort to pick it up again. It's also robust and easy to mesh our complex geometries inside Creo. So they use PTC Creo as their CAD system, and of course then the in Creo embedded version of SimCenter FlowAFD. The last one is an engineering service company, ZFW in Germany. They also have our larger test equipment, the power tester. The SimCenter power tester is for power cycling of power electronics. So we can run through 100,000 cycles and see how the device is failing over time and at which layer it is degrading due to delamination and so on. So they have the system where they run their tests, and with help of these tests on SimCenter FlowAFD, they say, with these findings from the study, using the combination of SimCenter Power Tester and SimCenter FlowAFD, reliable simulation models can be created and used in the future. Good. Now, let's recap here in the conclusions. So we have seen that modern businesses have challenges that require more agile product development approaches. So you can react faster to design changes and see if that design change makes even sense to further pursue or to just abandon it. The front-loading approach of the CFD simulation into the design process, so bringing it much earlier into the design process, enables these fast and agile design explorations. And you've seen that the SimCenter FlowUFT technology is made for ease of use for the designers and non-CFD experts. And therefore, also with the electronics cooling capabilities that I've shown you, you can see that it's really an ultimate set of electronics cooling capabilities. You might not need all of them. Therefore, they are split into separate modules. Depending on how deep you want to go into electronics cooling, you can get the full package, but you can also stay more on the surface level where you need fans, some chips, and importing a PCB or so. So now you have seen SimCenter FlowUFT in action in some of the videos. If you want to experience for yourself, want to see it on your application, on your models, feel free to contact us, getting a demo, training, and an evaluation so you can try it on yourself. With that, I want to thank you, and we can come